So I will be moving to Nottingham for a postdoc in late September. So I will unfortunately be parting with my many textbooks in this little library that I've built for myself over the course of my undergraduate degree, my master's, and now my PhD. So I thought it might be fun to do a textbook/resource recommendation video. The video will be broken down into different topics, so I'll timestamp it by subject and by the topic that I cover. The topics for this video in particular are my areas of expertise. So we have quantum mechanics, statistical mechanics, and quantum information theory, specifically for how it overlaps with the previous two topics. I will also put links to the books in the description that I recommend. So first off, I have my quantum mechanics textbook library. So we'll start there, and I will try my best to start from more of a beginner's introduction to more advanced textbooks and sort of frame, when and why you should use this textbook. So the first one that I will cover is Quantum Mechanics, the Theoretical Minimum by Leonard Susskind. And now this textbook admittedly doesn't entirely fit into what I'll be covering in this video, sort of a special aside, but I thought I'd mention it as I bought it, I think around my first year of undergrad to try and prepare for my second year modern physics course, where I went to school was your first look at quantum mechanics. Admittedly, at that stage of my education, I found this book actually quite hard to follow. However, the book is accompanied by a free lecture series that you can see online. The book begins with the Stern-Gerlach experiment, definitely one of my favorites, and tries to ambitiously take you from introducing quantum states, principles of quantum mechanics, all the way through entanglement and particle dynamics in about 300 pages. Which might seem like a lot, but here, as you can see, the font is quite big, and the book is not that thick. So to be honest, I wouldn't use this book as a primary resource to learn quantum mechanics. I think it'd be a very helpful book to add on maybe to your second or third year course to gain extra intuition, have some extra explanations, and sort of be a nice aid to an actual course in quantum mechanics. So the next book I want to talk about is Modern Physics for Scientists and Engineers by Thornton and Rex. So this book is good for anyone who hasn't seen quantum mechanics before as a topic. It reads a lot like a story that focuses on types of physics that were very hot topics and of course changed our view of the universe in the early 1900s and late 1800s. So it covers things like the kinetic theory of gases, special relativity, the black body radiation problem. The book introduces and carefully lays out open problems from this era and explains how they are resolved, giving a first look at an extremely large amount of areas in physics. Chapters 3 to 7 are good introductions to quantum mechanics, and of course the book doesn't end there. You will also cover things like atomic physics, statistical physics, even semiconductor theory, particle physics, and general relativity. So my main complaint at the time of taking modern physics and using this textbook is that it reads somewhat like a history book, with a lot of cool math sort of like mixed in, but the problems feel like you're somewhat inserted halfway through the problem or halfway through the theory. So some of the topics feel maybe mathematically unmotivated. So a lot of the times when I was doing the problems in this textbook, I felt like I didn't actually understand what I was doing. I just knew how to get from the point they inserted me at, perhaps to something that looked like the answer that was expected of me. But that shouldn't discourage you from being excited about this book or others like it. In the end, this book got me excited about quantum mechanics and made me want to do research in that field. Admittedly, though, it also introduced me to statistical physics, which at the time was sort of intimidating and not appealing. This certainly wasn't the book that convinced me to go into quantum statistical mechanics. So my conclusion here for this book is that if you are a second year and you don't know which physics topics you want to focus on, a book like this could be a good starting spot for you. So the next book is Quantum Physics by John S. Townsend, A Fundamental Approach to Modern Physics. So I bought this book while taking the modern physics course that I was just talking about because I was excited about the quantum mechanics portion of that book, and I definitely wanted a deeper understanding of it. This book does exactly that at that same level. It teaches quantum mechanics at around a second year level by introducing light, wave mechanics, and then exploring the Schrödinger equation. At the end, you will get a peek at things like solid-state physics, nuclear physics, particle physics, and special relativity, but it is much more specialized towards quantum mechanics. So if you want to specifically learn quantum mechanics at this level, I highly recommend it. It also definitely helped me prepare for my modern physics exams, as this allowed me to go deeper into the subjects at the same level as was expected at the modern physics level in second year. So the next textbook is Quantum Mechanics, A Modern Approach by Townsend again. So as you might have guessed, I quite like Townsend as an author. So here's another great book. This time it's actually at a higher level. If, for example, you are a third year or a fourth year who took a modern physics course, this can be your next step into quantum mechanics. The book starts out by covering the Stern-Gerlach experiment in detail. Definitely my favorite written explanation of the experiment that I'm aware of right now. It then takes you through rotations of bases and matrix mechanics, all which are motivated by the experiment that you just read about. It then covers angular momentum deeply, systems of two particles, more wave mechanics, the harmonic oscillator, which of course is an extremely important topic to learn, and it rounds off with topics like path integrals, perturbation theory, and more. So I personally find Townsend's writing very clear, the argument's easy to follow, so I definitely recommend this book if you have the required background. So if you're more of a senior or maybe a late third year student, fourth year student, this is a really good quantum mechanics textbook. So the next book I want to talk about is Principles of Quantum Mechanics, the second edition, or I guess the edition doesn't really matter, by Shankar. So I've never used this book formally for a course, but I found it useful as a reference for my fourth year courses in my graduate course in quantum mechanics. The book starts out by introducing mathematical preliminaries that are needed to understand the material, and then presents a good review of classical mechanics, or at least the classical mechanics that will be useful to you when you study this textbook. Once the mathematics and the problems with classical mechanics are laid out, we jump right into the postulates of quantum mechanics. I found this useful because I lean more into deriving my intuition from mathematics. So breaking down the theory into postulates and providing a good mathematical chapter to get you started worked really well for me. I think this is a good candidate book for self-study or as a book to supplement your studies if you need more context and explanation in a course not using it as a textbook. The rest of the textbook that I haven't described covers a lot of important topics, but by chapter 8 you are already learning the path integral, which is quite interesting. Chapter 10 starts covering systems of many particles, and there's a lot of really useful and relative topics in here like rotational invariance, spin, variational methods, perturbation theory, scattering, and even the Dirac equation. So I would recommend this textbook to fourth year students or early graduate students, but I personally use this textbook as a good reference to get a second explanation on topics I was seeing in fourth year and during my graduate courses. So the next book I want to talk about is Modern Quantum Mechanics by Sakurai. Now, this seems to be a favorite for a lot of fourth year courses or graduate courses in quantum mechanics. It has tons of exercises in the book. The explanations are mostly clear. To be honest, I think this is a good textbook to be coupled with a course and a set of lectures. I don't really have much else to say about it. It covers a lot of standard topics that you would like to see at the fourth year or graduate level. It's definitely a good book, but I found myself learning important concepts out of different textbooks while I was taking the class that was using this one. So the last quantum mechanics textbook that I want to talk about is my favorite. So it's the Quantum Mechanics book by, I hope I'm not butchering it, Auletta. So this is by far my favorite quantum book that's aimed at senior undergrads and junior grad students. Admittedly, I am biased here because I love the density matrix formalism of quantum mechanics, And quantum information is a big motivating factor in my field, so this is a great introduction to both. When I write videos with quantum topics for this channel, it's the first place I check, and usually the only place needed. The book starts from classical mechanics and tells the story of why we need quantum mechanics. It then does the standard introduction into wave mechanics, but does an excellent job reviewing the various pictures of quantum mechanics. By chapter 5, you're already dealing with density matrices, discussing pure and mixed states, along with compound systems or systems of multiple particles. It also, something that I like, pays close attention to the measurement problem, something that confuses all students, of course, and seems to be slightly hushed aside in most textbooks. The end of the textbook is dedicated to quantum information, so it doesn't really do path integrals, which of course is a minus for a course at this level, but it does cover a lot of topics that other quantum mechanics topics don't cover, so there is a trade-off here. So if path integrals are going to be a must for you, Shankar and Sakurai are great choices. If they're not, if you're going to something like quantum information, this is an amazing choice. So in conclusion, I would honestly recommend the 2 Townsend books, Into the Auletta book as my path from going from, a starting out level, a second year level, to a graduate level understanding of quantum mechanics. And that would be the path I would take personally for my own, research interests. But that is personally for my own taste. There are definitely other choices out there, like Shankar and Sakurai are obviously great choices. Next up, I'll cover books on statistical mechanics and thermodynamics. I'll cover these books somewhat in the order at which I personally received them, because a lot of them are really pitched at the same level or perhaps specialized in some way. So the first book that I wanted to talk about would be Statistical Physics of Particles by Kardar. This is a great first book for a number of topics. The first chapter is dedicated to thermodynamics, with a special attention given to topics that will be important later in the book. This book does have a very specific intention on the topics, which can be quite nice. But because of that, I would say this book should not be used as your first exposure to thermodynamics, but rather that chapter should serve as a good refresher for the topics needed to proceed in the book. You do get a whole chapter that's dedicated to probability theory, which is quite nice, and then it covers the kinetic theory of gases, then classical statistical mechanics, which includes topics on ensembles, and I quite like the equivalence of ensemble arguments given here. They are in particular very intuitive. I of course like the chapter on interacting particles. We tend to spend a lot of time in statistical mechanics on models that are solvable, so this is a nice inclusion. And then the rest of this book is focused on problems in statistical mechanics where the systems themselves are quantum mechanical. As a first look at statistical mechanics, I like this book a lot. When I was an undergrad at Western University, this is the book that they used for their graduate course in statistical mechanics, and I would say that makes sense. Statistical mechanics, at the end of the day, you need to be comfortable with classical mechanics and quantum mechanics to really make progress in the topic. So starting to study it around 3rd, 4th, maybe, during your master's degree, that does make a lot of sense to me. So this is definitely a senior undergrad to junior grad level textbook. I do think, however, that on its own, the topics covered here are a bit sparse. There's lots to cover in a statistical mechanics book, as we'll see later. This gets you through the basics pretty well. All in all, I would recommend it as a first book, and importantly, it sets you up for the next Kardar book, which we'll talk about next. So the next Kardar book is the Statistical Physics of Fields. This book takes you through classical field theory and studies phase transitions. It's definitely a must if you want to make a living or go into academia studying phase transitions. Definitely a good book. You'll learn crucially about the scaling hypothesis, which is incredible, and of course the renormalization group approach. Lots and lots of integrals to be performed, which is fine. Not my particular cup of tea, but some people like to do that during their day. And of course I would recommend this book to you only once you are more familiar with statistical mechanics on its own. This book takes statistical mechanics as a given and is more focused on using statistical mechanics to study phase transitions. So the next textbook that I want to tell you about is Statistical Mechanics by Berlinsky, an introductory graduate course. So this is my favorite statistical mechanics textbook. It is the one I use for my comprehensive exams, and I absolutely loved it. As far as statistical mechanics textbook goes, it has a great introduction chapter to thermodynamics, if that is something that you want more attention paid to. And of course, a biased take here, it simply jumps right into density matrices, which I think is an extremely natural way to describe statistical mechanics, in particular in the quantum setting. It covers everything Kardar's first book does for the most part, while adding in a large amount of chapters on extra things like Landau theory, real space renormalization, Monte Carlo, and more. It also gently touches on topics that the second Kardar book covers, while only really covering the essentials and doesn't go into the same depth. Overall, it seems like quite a self-contained, well-explained book that I highly recommend. Definitely an underrated book. If you want a one-size-fits-all book, which would take you through all of the topics you would expect for a 2-semester course on statistical mechanics, then this is your book. So next up is Pathria. This one definitely feels like a crowd favorite. I've never personally took it in a formal class setting, but it definitely gets bonus points, as this is the only book I'm aware of that covers the eigenstate thermalization hypothesis, sort of at an introductory statistical mechanics book level. Now, a huge upside for Pathria, it does put some effort into the dynamics. How do we arrive at statistical mechanics? Why is this description a good description? So a downside of most statistical mechanics textbooks is that they usually start with some type of axiom that basically gives you the microcanonical ensemble for free, so it assigns equal probability to microstates for an isolated system. Pathria goes past this and introduces how StatMech might emerge from dynamics, which is great. So that's definitely important to me, but not needed, of course, for most people. The foundations of StatMech are unimportant to most people, and instead, of course, the use cases are the most important part for the vast majority of people who use this topic in their day-to-day lives. The book overall gives you a great introduction to all the needed topics you'd like to have in a first course, and some extras for a second course. I can see why it's a fan favorite for sure. I personally haven't used this, as I said, for anything formal, but I like it a lot for the reason that it does actually cover a lot more about dynamics than most textbooks in this area, which I like a lot, including a chapter on non-equilibrium statistical mechanics. So the next book is somewhat of a strange one to add. It is Thermodynamics in the Quantum Regime. Way too many authors to name here. So quantum thermodynamics is an emerging and exciting field right now, and this book takes review articles or accessible first looks at topics from a wide range of authors, and it puts it all into one extremely thick book. If this sounds like an interesting field to you and you want to learn more, and you want to see what people are working on in a reasonably accessible way, and also assuming that you're comfortable with the books that I've shown you so far, then this is a good book to grab. So after covering all these books, what's my recommendation overall for different books on statistical mechanics? Well, all of these books here have their strengths and weaknesses. Personally, I like Berlinsky and Pathria as a good starting points to cover a wide range of topics, and then you can specialize from there. So last but not least is Quantum Information. Now, admittedly, these books are usually designed for people interested in quantum computing. I am not one of those people. I have read a bit on algorithms, of course, from these books, but this is not my area of expertise. My area of expertise is sort of an overlap between quantum information and quantum many-body physics. So the first book is Quantum Computation and Quantum Information by Nielsen. And this was my first exposure to quantum information, and I think most people would identify this as a pretty standard textbook that most people in the field have. The book on its own has a very useful introduction to quantum mechanics, and deals with quantum computing as its primary goal. For the most part, the explanations are really clear and easy to follow. I'd recommend this to anyone in about third year with a bit of quantum under their belt. Most concepts that you wouldn't know are covered well, or at least briefly, in the book if they are needed for a central result. So the next book is Quantum Information by Jaeger. So I had this book on my comprehensive exam. I found it easier to read in some places compared to the previous book, but a bit fast sometimes with how the topics sort of like went by. It does, however, introduce lots of central topics you might be interested in, like entanglement, multipartite entanglement, state tomography, communication, and so on. So I think it's a good book to get started on quantum computing and quantum information. I would rate this book as around the same sort of like area as the previous book by Nielsen. It's just shorter and perhaps with less topics. I do like the approach being a little bit more theoretical to start off though. Jumping right into qubits is actually quite nice. So the last book on the quantum info journey here that we've been having is The Geometry of Quantum States. So this is a book that I highly recommend. It introduces entanglement and the space of quantum states from a geometric point of view. It's definitely a completely different look from the last two quantum information books, which are more focused on getting you to quantum computing. This book instead is fully sort of dedicated to entanglement and understanding the probability distributions that we're studying when we study quantum mechanics. It's also quite rigorous mathematically, which is great, but the book is also very easy to follow, so that shouldn't be a downside if you don't like that. If you're interested in many body physics, and in particular entanglement, I definitely recommend this book. You can skip the other quantum information books as this is completely self-contained and sort of a separate perspective. So in conclusion, you can't go wrong with any of these choices. I think Jaeger and Nielsen are somewhat interchangeable as starting points, and then this geometry of quantum states sort of stands on its own. So that's all for today. If you're interested in many body physics, condensed matter physics, or statistical mechanics, check out my Discord server. The link's in the description. We're building a community there to chat about these topics. And as always, if you liked the video, don't forget to like, subscribe, and leave a comment below.